Sequences from real analysis. This is second lecture. So we'll be discussing the theorem after the definitions we have done in lecture 1. A sequence an is bounded if and only if there exists a positive real number m such that mod of an less than equal to m for all natural numbers, means for every term of the sequence. So we need to prove this result both ways. If sequence is bounded, this condition holds, and if this condition holds, sequence is bounded. So first listen about the bounded sequence. A sequence is said to be bounded if it is both ways bounded, that is if it is bounded above as well as bounded below. And for this, the mathematical way to write this is there exist two bounds of the sequence such that an is less than equal to k from upper side and less than equal to small k, that's the lower bound from lower side. And this condition is true for all natural number, means every term of the sequence is bounded between these two real numbers, small k and capital K. So then we say sequence is bounded. So here we are assuming sequence an to be bounded sequence. So by the definition of boundedness, I can write this. There exist two real numbers, small k and capital K, such that every term of the sequence is bounded between these two. So this is equation 1. We need to prove this result. So there should be existence of such m so that the mod an less than equals to m. So here we are assuming that m can be found from maximum of the positive quantities of these bounds, mod of small k and mod of capital K. So since m is the maximum one, so m will be greater than equal to both values. This is by the definition of maximum concept. And now to understand the modulus concept, mod x less than equal to a implies x lies between minus a to a. And this criteria hold both ways. And this is the definition of modulus. So applying the definition here, minus m to m will be the boundary for small k and capital K both. Now this is equation number 2. Combining 1 and 2. First I am writing equation 1, an lying between small k and capital K. Then from second I am taking this k less than equals to m and k small k is greater than equals to minus m. So every term of the sequence lying between minus m to m for every n. And now again applying the definition of modulus the reverse way, I can write this mod an less than equals to m for every natural number. Because why we are writing for every natural number? Because the condition of the sequence is satisfying for every natural number. So this is first part of the sequence. Applying the other part conversely. Conversely, we are assuming the such m exists, a positive real number m exists such that mod an is less than equals to m, and then opening the modulus part by the definition discussed above, an will be lying between minus m to m. So this capital M will work as the upper bound and minus m will work as the smaller bound, lower bound. So sequence is bounded both ways, hence the sequence is bounded, and this completes the result. So moving forward, least upper bound of a sequence, or we can say LUB, or we also say this as supremum, SUP. If a sequence an is bounded above, then there exists a real number k. Suppose I am writing k1 here. An less than equals to k1 for every n natural number, and k1 here is upper bound, means sequence is bounded from the upper side. Every term of the sequence is bounded from the upper side. K1 is called an upper bound of the sequence. Now take any number greater than k1. Suppose k2 is greater than k1. Then the sequence terms will also be less than k2. See, an was less than equals to k1 and k1 is less than equals to k2, means k2 is a bigger value. So an will also be less than equals to k2. So k2 here is also working as an upper bound, right? k1 was an upper bound and k2 since greater than k1 will also work as an upper bound. So any number greater than the upper bound will also work as an upper bound of the sequence. That's simple enough, right? So that means whenever there is a sequence which is bounded above, it cannot have one upper bound, it will be having infinitely many upper bounds. If a sequence is bounded above, then it has infinitely many upper bounds. So that means we are getting collection of upper bounds, and from that collection of upper bounds we'll be choosing the least one. So from the collection of all the upper bounds we have so far received of a particular sequence, if k will be the least, then k will be the least upper bound. K is called least upper bound or LUB of the sequence, right? So this is the criteria of selecting the least value from the collection of upper bounds. We are choosing the least one. So mathematically what we write for LUB definition, this you need to remember for theorems and questions. What are the properties that LUB follow? LUB of a sequence must follow these properties. First of all, it should be an upper bound of the sequence. As simple as that. Least upper bound should be a upper bound. It is an upper bound of the sequence. That is, every term of the sequence will be less than equal to this value, an less than equals to k for every natural number. Secondly, if I take epsilon positive, k minus epsilon will be a lesser quantity because epsilon is a positive quantity. K minus epsilon is very minutely less than k, and we will say that this lesser value of k will not serve as an upper bound of the sequence, then k will be the least, right? So for this we say there exists a positive integer small m, there must exist at least one, more than one can also exist, at least one should be there such that am is not less than equals to k minus epsilon. That is, am should be greater than k minus epsilon, because if am would be less than equals to k minus epsilon, then k minus epsilon will start working as an upper bound, then k won't be the least one. So for this we are saying k minus epsilon, which is the slightest lesser value than k, will not work as an upper bound of the sequence. That means k is the least upper bound of the sequence, because there exists one term of the sequence which is not following the definition of an upper bound with k minus epsilon. So k minus epsilon is not working as upper bound, k is the least one. So next is greatest lower bound of the sequence or GLB, infimum, INF. If a sequence is bounded below, then it has a lower bound. It has a lower bound. There exists a real number small k1 such that k1 less than equals to an for every n natural number. Since every term of the sequence is greater than equals to a particular value k1, if I'll be choosing the number less than k1, k2 is less than k1, so combining these condition, k2 is will always be less than equals to an also. So that means k2 is also serving for the lower bound of the sequence, right? Suppose this is the sequence, k1 is the greatest one, then k2, then k3, and this is infinite sequence we are getting of lower bounds, and from this collection k1 is the greatest. I'm taking k1 as k itself. So k1 or k is GLB of the sequence. So in words we say, if k2 is a lesser quantity than k1, k2 is a lesser number than k1, and since all the terms were greater than k1, so all the terms of the sequence will also be greater than k2. So k2 is also serving as a lower bound of this sequence. k2 is also a lower bound of the sequence, for which k1 was working before as lower bound of the sequence. Now k2 is working. So any number you choose less than k1, once you have found the lower bound, any number less than lower bound will also work as a lower bound of the sequence. Any number which is less than k1 will also work as a lower bound of the sequence. That means once we are able to find a lower bound of the sequence, we are able to get infinitely many lower bounds of a particular sequence. Any number lesser than lower bound already existing will also work as a lower bound. So from the collection of this lower bound, we'll be choosing the greatest one. If a sequence is bounded below, it has infinitely many lower bounds. So of all the lower bounds of the sequence, if k is the greatest one, if one particular value I am choosing which is the greatest of this collection, if k is the greatest one, then that particular small k is greatest lower bound or GLB of this sequence. So the GLB must follow these following properties. GLB of a sequence has following properties. Mathematically, you need to remember these two conditions for doing theorems and questions further. One is it is a lower bound of the sequence. That means every term of the sequence is greater than equals to that particular value, small k less than equals to k an for all n natural. Secondly, any number slightly greater than that value will not work as a lower bound. So small k plus epsilon, which is greater than k, because epsilon is a positive quantity, k plus epsilon is greater than k. There exists at least one positive integer small m such that the mth term of the sequence will not be following the lower bound definition with L plus epsilon. That is, am will not be greater than equals to k plus epsilon. That is, am will be less than k plus epsilon. So we are having a particular term, at least one term in the sequence which is not allowing k plus epsilon, which is not allowing k plus epsilon to be the lower bound of the sequence. So k plus epsilon is not lower bound, k will be the greatest one.